I'm David, and with me today is Sophia, and we're going to get into a really interesting question today. Why hasn't cloud gaming just completely taken over and replaced our consoles and high-end PCs?
It's great to be back. And yeah, it's such a critical question. The promise is huge, right?
Totally.
The idea of playing the latest, greatest AAA titles on literally any device.
Your smart TV, a cheap laptop, anything.
Exactly. And this whole movement, it was really driven by the fact that game hardware requirements just kept going up and up.
Oh, and then the pandemic hit, and component prices just went through the roof.
Precisely. So the ambition is there, but the physics of it all are pretty brutal.
So what is that single biggest thing, the one roadblock that's preventing this dream from just being everywhere?
It all comes down to the network. It's always the network. We're talking about, massive bandwidth needs and maybe more importantly, latency. Cloud gaming is basically just video streaming, but it's interactive. So if you press a button to shoot, that signal has to go all the way to a server. The server has to process it, create a new video frame, and then stream it all the way back to you.
And for that to feel right, for what I think researchers call the quality of experience, or QoE.
Yes, for the QoE to be good, that whole loop, the end-to-end latency, it absolutely has to stay below 50 milliseconds.
50. That is a razor-thin margin for error.
It is. And the core of the problem is just the sheer size of the data. The biggest strain on the whole system is that raw video feed.
Okay, so quantify that for us. How big are we talking?
Okay, so let's say you're sending raw 1080p video at a pretty standard 30 frames a second. That requires something like 237 megabytes per second.
237.
Yeah.
So without some kind of cheat, cloud gaming is it's dead on arrival for most users.
Exactly. I mean, if you compare that 237 megabytes per second to the average bandwidth across, say, the European Union, which is about 13, you see the massive gap.
You can't fit it.
You can't. So you're forced to use traditional video compression like H.264, but that's inherently lossy. You lose quality, which is the last thing you want.
Okay, so before we get into how AI is basically proposing a cheat code for physics, welcome everyone to TechDaily.ai. You can sponsor this analysis for just $25. Your message will be featured across major platforms like Apple Podcasts, Amazon Music, Spotify, and more. If you're interested, visit TechDaily.ai to get started today.
So if we can't just throw more bandwidth at the problem, we have to get clever, and this is where that AI proposal comes in. It's something called lossless resolution upscaling.
This is the real innovation here. The whole idea is to cheat the data transfer. So instead of the server rendering the game at a full 1920 by 1080...
So full HD.
Right. You render it at a much, much lower resolution, something like 960 by 540 pixels.
That's a quarter of the size.
Exactly. A quarter of the data. You stream that tiny little feed, and then a neural network on the client side. So running on your laptop or your TV uses AI to blow it back up to full HD quality. And that's fundamentally different from what I do when I just take a tiny image and stretch it on my phone. That always looks terrible.
Oh, completely different. Traditional methods like bilinear or bicubic filtering, they just interpolate. They're guessing where the new pixels should go based on what's around them.
Which is why it gets all blurry and you lose all the sharp edges.
You lose all the high-frequency details. But AI is different. It's been trained on just vast amounts of data to recognize patterns. It doesn't guess. It tries to recreate the missing information based on what a high-res image should look like.
Okay.
We can even look at a specific algorithm like FSRCNN.
The Fast Super Resolution Convolutional Neural Network.
That's the one. It's a neural network that's been really optimized for speed to run fast on your device.
And what's its secret to being so fast?
A couple of things, really. First, it takes the low-res image directly. Older algorithms needed this extra pre-processing step, which slowed everything down. This one skips that.
Okay, that makes sense.
And second, for efficiency, it usually only upscales the luminance.
Just the brightness. Why only the brightness?
Because our eyes are, frankly, not that great at noticing subtle differences in color, the chrominance, but we are incredibly sensitive to changes in brightness.
So you apply the heavy AI lifting only where we'll actually notice it.
Exactly. You save a ton of computational power, and the final image quality, to our eyes, looks almost just as good.
All right, so let's see if this theoretical physics cheat actually works in the real world. They tested this, right? I think with a custom platform streaming CSGO.
They did, and the results were pretty transformative, especially for data efficiency. They ran two setups, one streaming native 1080p, and one streaming that tiny 960 by 540 version and then upscaling it.
And the result?
The upscaled version. It achieved a mean bitrate reduction of a staggering 61.37%.
61%. So that's it. That's the trick. You just saved almost 2/3 of the data.
Yep.
That instantly makes cloud gaming viable for people with terrible internet or, expensive data plans.
Yeah.
That reduction in data has to improve latency too.
It does. And that's just the benefit on your end. Think about the service provider.
Right, the server side.
Rendering the game at that much lower resolution just slashed the GPU load on the server. When they ran it at native 1080p, the server's GPU was unstable. It was peaking near 100% capacity.
Working way too hard.
But the low-res version, the GPU load stabilized in this really efficient range between 30 and 45%.
So wait, that's like a 50% efficiency improvement for the company running the service?
It is.
They can host double the number of players on the exact same hardware? That completely changes the economics of this whole model.
It's a win-win. Better economics for them, better accessibility for you.
But there is always a catch, isn't there?
Yeah.
What was the sacrifice for that incredible efficiency?
Image quality. It's always a trade-off. Now, the researchers said the overall quality was quite high, which is amazing considering you're working with 75% less information.
Yeah.
But they did find noticeable defects, a little bit of a color shift, and more importantly, some distortion on small details.
Can you give us an example of that? What kind of distortion?
So in the CS.go test, core parts of the user interface, the minimap, your health bar, they were heavily distorted, kind of dented.
Oof. That's a problem. If you're playing a competitive shooter, you need to be able to glance at your minimap and get information instantly.
And if it's distorted or your health is hard to read, it's unacceptable for competitive play.
So that's a really critical limitation. This can't be something that's just on by default for everyone.
And that's the conclusion they reached. Upscaling is incredible for latency and efficiency, but providers have to be careful. It should be an option you can toggle.
For the casual player or someone on a bad connection.
Exactly. Not the mandatory standard if you want to keep your hardcore gamers happy.
Okay, so that sort of moves us from solving the data size problem on the device to solving the delivery problem in the network itself. Because even with a 50% data cut, you still need smart pipes to deliver it.
Right. This is where we start looking at beyond 5G networks and how they guarantee performance for things like gaming, VR, and AR.
And how are they doing it?
They're bringing the AI into the very core of the network architecture. So you have a part of the network called the user plane function, the UPF. Think of it as the network's main traffic cop.
Okay, the traffic cop.
They're basically instrumenting that traffic cop with a special filter.
And what's this new filter doing?
It's measuring the latency for every single person's session in real time without getting in the way. It analyzes packet timestamps. It's called time shift latency estimation. And it knows moment by moment exactly how much delay you, the listener, are experiencing on your connection.
Okay, so now the network has this constant fire hose of super specific latency data. Where does it all go?
It's fed directly into something called the Network Data Analytics Function, or NWDAF.
The predictive brain of the network.
That's a perfect way to put it. This brain is full of pre-trained machine learning models. They found one called Cat Boost was super accurate, like 95% accurate.
And what does this brain learn to do with all that data?
It can accurately classify what game you're playing.
Just from the network traffic.
Just from the patterns. It knows if you're playing League of Legends or Valorant or Teamfight Tactics just by looking at the data flow.
So let's connect the whole chain then. The system knows the user is playing Valorant, and the AI brain sees their latency just spiked past that critical 50 millisecond mark.
Exactly. And because it knows what game you're playing and what your real-time latency is, the NWDAF, the brain, can immediately notify another part of the network, the session management function, which is the action trigger.
And what does it do?
The SMF can instantly take corrective steps. It can dynamically reroute your data to a cleaner path or reallocate network resources just for you. And this all happens before you, the player, even notice the lag. It's proactive.
It's predictive maintenance for your gaming session.
That's it.
That's a huge shift in how networks operate.
Yeah.
And it's so vital when you look at the landscape in 2025. You have Xbox Cloud Gaming, NVIDIA GeForce now with their monster RTX servers, PlayStation Plus.
And we all remember the ghost of Google Stadia, which reminds us that execution is everything.
For sure. And the debate today seems to be that, consoles and PCs still dominate for the hardcore competitive crowd.
They do. It's about reliability and that feeling of ownership. But the cloud excels for the casual gamer. It's about affordability, instant access, and playing on any device you happen to own.
So where does this all lead in the long run? Is the console going to die?
All the signs are pointing overwhelmingly to a hybrid model. They're going to coexist. The boundaries are just disappearing. The focus is shifting to freedom of access, not locking you into buying a specific box.
And now AI's role is moving beyond just delivering the game and into creating the game content itself. We're starting to hear this term, living games.
This is maybe the most exciting part of it all. We're moving away from these static, finished products. Living games are games that can dynamically adapt and evolve in real time.
Wow.
This helps cut down the massive costs of development, but it also offers, potentially infinite content and stories.
And we're seeing this happen right now, aren't we? Capcom, the company behind Resident Evil.
Right. They're using Google Cloud AI and Gemini to just rapidly generate and test hundreds of thousands of ideas for items, for environments.
They're cutting costs and just speeding up their entire development timeline.
And then you have something even wilder, like Clang games. They're using AI models to power hundreds of thousands of autonomous virtual people, they call them seedlings, in their online game.
And these seedlings, what do?
They have unique personalities. They form their own emergent societies through natural conversations with players and with each other.
So generative AI is removing that bottleneck of creative labor. It frees up artists to focus on the big picture, the really creative challenges.
And to adapt to what players are actually doing in their game in real time, instead of being locked into a rigid, expensive design from 5 years ago.
So if we bring this all together, machine learning is fixing the fundamental economics of cloud gaming.
Absolutely. That client-side upscaling gives you a 61% bandwidth reduction, a 50% server efficiency boost. That alone makes cloud gaming viable for a huge new global audience.
And the AI inside the 5G network ensures that the quality of that experience stays high no matter what.
It's guaranteed.
So the big takeaway for you, the listener, is that in 2025, cloud gaming isn't some experiment anymore. It's a core pillar of the industry. It's not about replacement. It's about coevolution. And it's all being driven by AI.
Which leaves us with a pretty provocative final thought.
Go on.
If AI can drastically reduce the cost of streaming games, while at the same time generating infinite, unique, and adaptive content inside those games, does the whole concept of a finished game, a static thing you buy on a disc, does that just become completely obsolete? What does it even mean to own a game that never, ever stops changing?
A truly philosophical challenge for the future. Thank you for guiding us through this.
My pleasure.
And thank you for joining us. We'll be back soon with another exploration into what you need to know now.